When we say, think of this in algebra, nothing changed. Remember, I told you calculus is nothing more than turbo algebra. In algebra, we discussed extreme values. What do you think that means? What is an extreme value? Yeah, the maximum or minimum value of a function. That's pretty much it. So let's look at their definition. Let's look at their definition of. Oops. So here's their definition. That f of x be a function with domain D. Good morning. I don't know where he's. At least you're here. Then f has an absolute maximum value on D at a point C if. So here we're looking for absolute maximum. So what it says is for all other x's, it has to be less than that value. For every x in D. See if you guys are. Oh. Remember what these symbols mean. This means for every x as an element in D. So every x inside the domain. If you think about it, this is the y-axis, this is the x-axis, this is my value C. So f of C is the highest point. That means all these other x values to the left and to the right of C, all of these f of x's have to be less than f of C. So if that's the case, then we have a maximum. So that's an absolute maximum. And we have an absolute minimum value on our domain D at our point C if all of our x values are larger than our value at C for every x in D. So that graph will look like this. Here we have f of c. That means all of our x values on both sides are above f of c, or greater than f of c. So far, so good. Negative pi over 2 to pi over 2, and that's 1. So what function do you think that is defined by that graph right there? Has a beginning and endpoint. What function do you think is that?
Square root.
Yeah, it could be square root, negative square root. No, not square, negative square root is squared.
Yeah.
It would be negative x squared plus 2. You could do that, but it's from negative pi over 2, pi over 2. So what function has x-intercepts at pi over 2 and a maximum at 0 as 1? Very good. So it's cosine, and what's the domain?
Negative pi.
Right. Now, in that same domain, what would sine look like? What would sine look like? Well, at negative pi over 2, what's sine? Think about it. Let's look at the unit circle. One. This is 1 comma 0. This is 0 comma 1. This is negative 1 comma 0, 0 comma negative 1. Which one of these values corresponds to the sine value? The y values. So this is at 0. This is at pi over 2. This is at pi. This is at 3 pi over 2. And this is at 2 pi. So at pi over 2 and negative pi over 2, what sign? 1 and negative 1. So at negative pi over 2, it's negative 1. At 0, what is sign? 0. And at pi over 2, what sign? So that's the sine function. Okay, so the cosine function. Do we have an absolute max or an absolute min? Do we have an absolute max on cosine? Yes. Where?
The 1.
Yeah, x equals 0. Right. When equals 1. So whenever you talk about that, you said it's a maximum at x equals 0. It's the x value that gives that value its maximum point. Do we have a minimum?
Same.
Absolute means what? Yeah. One and only one. Typically, that's what we say it. Because if it's absolute, then there's nobody else greater than or less than, or nobody else equal to. So all we have here is an absolute maximum. How about the sign? Do we have an absolute max? Absolute min?
Yes.
Yes and yes. So we have an absolute max at x equals pi over 2. And then we have an absolute min, which is the lowest point, at x equals negative pi over 2. So the maximum is positive 1 at that, is negative 1 at that. Now, what we have to look at here is this. We have endpoints. When you have endpoints, what does that tell you about your domain? Domain is bounded. Very important. We'll talk about this in a second, why it's important. But your domain, you have to have beginning and endpoints. What else has to be important in there? The endpoints have to be defined, it's bounded. The function, all these functions we talked about so far have to be continuous. Think about it. That should be open source. That's closed. In our domain from A to B, do we have a maximum minima? No, we can't say anything because it's not continuous. We have two separate subfunctions in there, so we'd have to change the domain in order to talk about those. So, Bate was saying here, a function may not have extrema points if the domain is unbounded or it doesn't have any endpoints. So what does that mean? What does unbounded mean?
It's infinite?
Yes. Yeah, both of those. Very good. Yes. Unbounded means they're open and it could go to infinity, negative infinity. Or we can go -2 to 5, something like that. But they're open intervals. Unbounded, one of our first thing, when we think about unbounded, it goes to infinity. The second thing, it's unbounded because there's no end to it. Can we get to 5 on this, in this interval here, this domain? Can we get to number 5? No, because it's not included. What's the biggest number we can get to in this interval? We can't do 4.1? We can't do 4.99999. Yeah, so so the highest we can go is 4.9 forever. So that's unbounded because there is no end to it. So since it's unbounded, it has no endpoints. There's no end. There's no end to how many decimal points I can put in the 4.9999999. All right. Let's look at how this works with respect to, let's look at our function x squared. There are four possibilities we can do with this function. All of these have the same graph. They're all x squared. So in the first one, this is our domain. Our domain here is between 0 and 2. Our domain here is between 0 and 2. In the first one, do we have absolute maximum min? Which one? Or both? Right, so we have an absolute min right here. It's the lowest point. How about the next one? What do we have there? Yep, we have an absolute max right there, and we have an absolute min right there. How about this one?
A max.
We only have an absolute max because we can never get to the lowest point here. We can always go 0.000000001, 0.00000. So we will never get to the value 1, so we don't have a minimum. And since both of these open, no max or min, because we can never get to the endpoints. So you see that continuity and boundedness are very important in determining extrema.
You use like a limit.
Ooh, good question. Can you use limit functions to talk about extrema? That's a very good question. Let's discuss that. Can we use the limit function to find an extrema? Remember what we said, remember the first example when we talked about limits? This was our limit, right? Does it exist? Limits don't have to exist, to be there. It simply has to approach it. That's why we cannot talk about limits and extrema points, because extrema points have to be physical numbers, physical points. And limits simply have to approach it from both sides. Good question, but no, you can't take limits We cannot talk about limits and extreme at the same time. Very good question, actually. All right, let's look at our first theorem. The extreme value theorem. If f of x is continuous on our closed interval, then f of x has both an absolute maximum m, oops, and an absolute minimum, bless you, little m in the closed interval. This is the first part. If f is continuous on a closed interval AB, then f of x, the function itself, has both an absolute maximum and an absolute minimum in that interval. Can they be the same? Or a horizontal line? So it's, yeah, so we look at that, but it has to be in an interval. And you're right, it could be a point, and that'd be both a max and min. So we have to go further now and define even further the stuff we leave off on. That means there are numbers x1 and x sub 2 in the interval AB where f of x1 equals the minimum n and f of x2 equals the maximum value. Remember, big M was the absolute maximum, little m was the absolute minimum. So m is less than equal to our function is less than equal to our upper bound for every other x in the domain of AB. So the minimum is less than the function is less than equal to the maximum for every other x value in the. So what does that mean? Let's look at this and let's interpret what it says. What are the conditions that have to exist here? What conditions have to exist for this theorem to be true? In the first line, what does it tell us?
Continuous domain in a closed interval.
It has to be continuous. The function has to be continuous on the closed interval. So those two conditions have to exist, because notice, once that exists, then we have both the maximum and minimum. The maximum is gonna be greater than the minimum. Duh, or less than equal to, I should say. As we said earlier, remember, can they have them both the same? Yes, you can. You can have a maximum and minimum be the same value. So conditions that must exist for extrema values to exist. This is according to theorem 1. F of x must be continuous. Is there a maximum in this function? Isn't there, let's make this. There's a maximum here for this first interval and this interval here at B. So we have two of them because the function is not continuous. Our interval is no longer A and B. Our interval is now A to C and C to B. Now we have maximums and minimums. So you cannot have the function has to be continuous. If it's not continuous, then we cannot be sure about a maximum or minimum to exist.
C was open.
Well, either way, it's not a continuous function because going from A to B, there's a jump discontinuity here. So once that happens, we can't use that domain. We have to redefine the domain and then we can move on. Then, yes, then they become subdomains. The interval must be finite. What does that mean? Right. It cannot go to infinity. Or something else. In other words, cannot go to infinity or plus or minus infinity. Or what else? Cannot be open. But yeah, that's true. Cannot be imaginary either. In other words, you cannot, you notice, yeah, that's a good point. None of these examples we've ever seen are imaginary. Can you take a derivative of an imaginary function? It's imaginary. You can't because, well, you can think about it, but you can't do it. So the function has to be continuous. The intervals must be finite. And the interval must be closed. This was important because once you said closed, that tells you you can never have an open interval. So this one here has example 1. Here's A. So we start off. Do we have, here, name label B. Do we have a maximum minimum there? Do we have absolute maximum minimum? Yes, this is the lowest and this one's the highest. It's the bad graph, but. So what we have to do, we have to compare, make sure those numbers, make sure that the values themselves are higher. And that's going to be important later on. Do we have maximum minimum there?
Yeah.
Yeah. That's the maximum, that's the minimum. This is the highest, so we have a maxima here. Do we have a minimum? Yeah, this is the lowest point, so that's my minimum. Here, we obviously have a minimum down here. Here we have a maxima there at the end point. So what do we notice about these four pictures? Why are these four pictures important? Where can extrema occur?
Terms.
Okay, and yes, okay, so notice how we're always inside the interval AB. Yes, they happen in terms inside the interval, right? Since they happen inside the intervals, we call these interior points. So we call this one x1, we'll call this one x2. We'll call this one x1. It's an interior point. This is x1. Those are all interior points. So we know that extrema can happen in interior points, max and minima. Where else can they occur? Where else can extrema occur? At endpoints, yes. Here we have at endpoints. So whenever we're talking about extrema, we have to look at three parts. The endpoints, A and B. And then we have to look at any internal points where the function has a point, a curve changer. And that's going to be important when we start looking about these. How do we find these values? Do you have to have extrema points? Can you think of a function that doesn't have extrema points? Well, there's a whole bunch of them. The cube function. The cube root function. Exponential function. What does the exponential function look like? You're thinking square root. The exponential function, it goes on from negative infinity to positive infinity. Well, we know that because what's the domain of the exponential function? Can we have from negative infinity to positive infinity? No. Is it a continuous function? Is it a continuous function? Yes, there's no breaks in there. Is it unbounded? Yes, and we can't have that because our domains have to be within a closed interval. Because we can't check the endpoints on an unbounded interval. So that's why it has to be continuous. It has to be a very, very, very important factor of it. Is continuity important? Here's A. Here's B. Do we have a maximum minima in that function? The interval is AB. It's closed, isn't it? Do we have a maximum minima? We have a minima here. Do we have a maxima? Nope. Because even though it jumps down here, this is not a minima because this is simply a point. The function itself goes up here and then it stops. Right? We can't get to it. So those are absolute. Absolute extrema occur in the interval. How many times do they occur? At most one time. You cannot have two absolute maxima. Think about it. You cannot, if it's absolute, you can only have one absolute ruler. You cannot have two or more. So whenever you deal with absolutes, you can only have an at most one time. We showed the examples. Max extremes only happen at one time. Then we could look at what's called a relative extrema. Can occur multiple times in the interval. What's the difference between absolute and relative? Have you ever heard that before? Relative extrema? Relative extrema is defined on a subinterval of the domain. Defined on a subinterval of the domain, the overall domain. What does that mean? So the perfect example Does that have absolute maximum, absolute minimum? Well, actually, yes and no. Does it have absolute maximum minimum? Yes. But at the same time, no, because what's missing from that statement? Yeah, I don't have any endpoints. Right now, when I say cosine of x, what's my domain? Right. But if I say instead of this, I can't use that. Let's say I want from negative 2 pi to 2 pi. So we look at the graph. We have pi over 2, pi, 3 pi over 2, 2 pi. Negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. And the amplitude is 1, negative 1. So cosine looks like this. So now does it have an absolute value? No. But this point here, this point here, this point here, we have relative maxima and minima. Because think of it, for the interval from negative 2 pi, negative 2 pi to, let's say, negative pi over 2, do we have a maxima minima in there? Yeah, the maxima is there. The minima is there. But is it an absolute? No, because the overall domain is from negative 2 pi to 2 pi. This is simply a subset of the other one. So you can have multiple relative maximum minima, but you only have one absolute maximum minimum. Makes sense? Okay. Let's define these. A function f of x has a local or relative maximum at a point C within its own domain D. If f of x is less than equal to f of c for every x in our domain. In some open interval containing C. So relative and local minimums, we normally call it in math, call it relative minima, relative maxima, because it's relative to the subdomain it's being defined under. Other people call it local because it's local in this small neighborhood. So f of x is a local minima, maxima, if at any point C, f of x is less than C for that x in those domain, in that subdomain. This is our subdomain. This is our main domain. So this is the domain where it's defined. We could even say, we can use open parentheses now. In some open interval containing C. Why? Okay, here's a question. Why does it have to be in some open interval containing C? Because if it's relative, if it's a local extrema, if it's local, that means it just can't be looked at over the entire domain. So if the domain is from negative 2 pi to 2 pi, then isn't this a subdomain? Isn't this domain smaller than this one? Yeah, because you can't use the endpoints. So that's what we're saying here is, because if we're looking over the entire domain, then we have to stick with those rules. We now we're dealing with local, relative ones, so it's got to be a subset of the overall domain. So that's a relative maxima. It's just the opposite when it comes to a minima. F of x has a local or a relative minimum value at C within its domain D if f of x is greater than equal to f of C for every x in D. In some open interval containing C. Why is it equal? Why isn't it strictly f of x is strictly greater than f of C? Because remember, the critical, I'm going to use those words just yet. The extrema can happen at the endpoints. So the values that we pick can be endpoints. Okay, what is an extrema? What does extrema mean? Because we talked about maximum and minimum. Maximum, minimum, maxima, minima. Extremum going to extrema. This is singular. This is plural. So when you say maximum, it's singular. When you say maxima, it's plural. When you say extremum, we're talking about singular, only one value. When we say extrema, that means it could be multiple of them. Before we jump into the theorem, we have a function. Here's f of x. It's a continuous function. It has a maximum and a minimum. So remember, this is the function f of x. How do we find the maxima and minima points? Extrema, if you think about these, what do we call the point that's highest or lowest on a curve? What's another name for those?
Good.
What is it? It's the vertex, the vertices. Since it's a vertex from algebra, what's the slope of the curve at the vertex? What's the slope of the curve at a vertex?
0.
0.
Right. So the first derivative, which is the slope, we set it equal to 0.
I have a question.
Yes.
Would this be a critical points or yeah, right? Because it's a 0, the derivative.
Why'd you use the word critical point?
I remember like hearing
I
about it.
know, I know. So since we haven't discussed it yet, don't interject those words. Yes, I can tell when somebody had it before. So I'm not going to do that yet because then I'm jumping in for other people who haven't had it before. So I'm not going to answer that question because we haven't discussed critical values, critical points yet. Theorem 2. The first derivative theorem for local extrema values. So let f of x be a continuous function on a closed interval if f of x has a local max or min value at an interior point. What's an interior point? What's an interior point? Why do they call it interior point?
They're within the bound.
Yeah, because the bounds are from A to B. Anything inside there are interior inside the interior of that domain. So local maximum minimum value on the interior points that C of the domain of f of x And if f prime of x is defined at C, then the derivative of f at C equals 0. So f of x is a continuous function in that domain. If it has a local max or minima at some value, interior value C, then we know it's a maximum in extrema if the first derivative of the function at that value C equals 0. Because the value we're looking for is where is the slope equal to 0. Let's look for an example. Yeah, we're good. So here we have x or C1 and C2. What the definition? Let's see. So extrema points can occur at where? 1, x equals A, x equals B, x equals some interior points x or C inside the domain. So we know that already. Let's see how it relates to what we just learned. Slope is 0. The function, the first derivative of the function equals 0. Tells us we have a vertex, which is an extrema. So extrema points can exist when the first derivative of x equals 0, where x is that's the first point. F of A, not this. The derivatives don't matter at the endpoints. Why don't the derivatives matter at the endpoints? Because that's also going to bring us to the third one. Why doesn't the derivative, it matters if we have interior points. Why can't we use the same logic for endpoints?
Is it because you can't find the left or the right limit?
Beautiful, exactly. Because at the endpoints, we cannot find, in order to find a derivative, it has to approach from both sides. And since we can't, so all we can do here is simply look at the values for f of a and f of b. Very good. And then another place so when we start doing the examples, what we're going to look at when we try to find extrema points, we'll first plot in a and b, see what the values are there. We'll take the first derivative of the function, see where it equals 0, and see where it's undefined. And then we'll test those values. Now, those values, the x values that make the first derivative equals 0 or undefined are our critical values, or we can find critical point. Why are they called critical? Because that critical simply means important. Out of all the x values in our domain, these are the ones that are the most important. So that's why they call critical values are critical points. The actual point themselves where it exists. So this is what we'll have to do whenever we start searching for maximum minima. Ooh, here's a question. A statement. A function can have a critical point at some value c without having a relative extrema at that point. A function can have a critical point at some value x equals c without it being a relative and extrema at that point. Case in point. Because if we look at this thing very, very closely, if we take the first derivative of this, What do we get?
3x squared.
Set that equal to 0. What does x equal?
1/3 square root.
Divided by 3, it's still 0. Square root of 0 is still 0. So that means our critical value is x equals 0. We just talked about if we have a critical value, that means it's an extrema point. Extrema points are maxima minima. Is this a maxima or minima? Neither one. It's actually both. If we look at it coming from the left side, it's a maxima point. If we look at it coming from the right-hand side, it's a minima. But since it's both of them, x equals 0 is what we call a point of inflection. Point of inflection is where the graph has both a maxima and a minima at the same spot. Because an absolute extrema must occur at a critical point or at an endpoint. And we're going to look at more into extreme points of inflection later on. There's a much easier way to find those and what they really mean. Example 2. Find the absolute extrema of f of x equals x squared on the interval -2, 1. Okay, good. Find the absolute extreme value in that domain. So how do we find the absolute extreme of points? The first thing you got to do is at the endpoints. What are the values? So we have f of -2 and f of 1. So -2 squared is equal to 4. 1 squared is equal to 1. So those are the values at the endpoints. Now we look at interior points. Which interior points do we look at? Well, we take the first derivative, set it equal to 0 first. So if the first derivative is 2x, set that equal to 0, x is equal to 0. So we look at the value of the function at 0. So we have 0 squared is 0. Are there any places that makes the function undefined? No, because it's a quadratic equation. So all we have to do to find the extrema points is look at these three values in this case. So what's the absolute maximum? What's the biggest number? 4. What's the absolute minimum? 0. So those are our absolute extrema. So again, whenever you look for extrema points, you first plug in the endpoints, take the function, set it equal to 0, find the critical value or critical point, and then see where the function's undefined. And at those 3 points, or those 3 sections, that's when you can see where the extrema points are. Example 3. Find the absolute extrema of f of x equals 10x 2 minus ln x on the interval 1 e squared. All right, so the first thing we do, at the endpoints, the endpoints, do we take the first derivative of it? No. Endpoints, just plug them in as it is. So we have f of 1 and f of e squared. So we have 10 times 1, 2 minus ln of 1. What is the ln of 1? What does the graph of ln look like? The graph of ln looks like this. So when x is equal to 1, the value is 0. So the value is 20. Then at e squared, we have 10 e squared 2 minus ln e squared. It looks ugly, doesn't it? Think you need a calculator. You don't. So we have 10 e squared. What's the rule about natural logs? Whenever you have a logarithmic function and it has an exponent, that exponent goes out in front. 2 minus 2. ln is the same thing as log base e. So that's log base e of e. There's a property in logarithms that whenever the base and the operation are the same, they cancel out. It equals 1. So this is equal to 1. So we have 10e squared, 2 minus 2. 2 minus 2 is 0, so the whole thing is 0. So those are the endpoints. The critical point. How do we find the critical point?
You find the first derivative and set it to 0.
Find the first derivative, very good. Set it equal to 0. So the first derivative, it's a product rule, so we got to do the product stuff. Actually, let's see. What if we distribute this? We get 10 times 2 is 20x minus 10x ln x. Now we take this apart. The derivative of 20x is what?
20.
20, because x goes away, so it's 20 minus. Now we have a product rule. So it's minus this product rule, so it's 10x ln x. Derivative of 10x is 10. What's the derivative of ln x?
1 over x.
1 over x. Multiply those out, so it's 10 ln x. Since it's product, we plus 10x times 1 over x. Ln x. X's cancel, so we have plus 10. They both have a 10, so we can factor that out. So we have ln x plus 1. So where does that equal 0? So move this whole equation here to the other side. So we have 20 equals 10 ln x plus 1. Divide both sides by 10. So it's 2 is equal to ln x plus 1. Subtract 1 from both sides. 1 equals ln x. Anybody know how do we figure this one out? How do we figure this one out? Using a calculator, you don't need it. Ln x equals 1. Ln x is log base e of x is equal to 1. The conversion from logarithmic to exponentials, take the base, push it there, so it becomes So this log falls off, so it's x is equal to e to the power 1, which is just e. So that's what so we plug that back into our function, which is our function 10x 2 minus ln x. Plug e in place of there, which becomes 10e 2 minus ln e. So it's 10e. What's ln e? We just talked about that. ln is log base e of e, so that equals 1. 2 minus 1 is 1, so it's simply 10e. So this is our third value. So where's the numbers? So our values are at 1, it equaled 20. At e squared, these are the endpoints, it equals 0. And at e, it equals 10e. So do we have an absolute max? Do we have an absolute min? What's the smallest of all these three numbers? 0. Remember, what does E equal? E is a constant, 2.7187. So it's 10 times 2.7, which is going to be bigger than 20. So it's going to be 10E. It'll be 27.1. One more example. And besides, don't feel bad. If you get stuck in these things, use a calculator to do the calculations for you. But again, you see, you don't need calculators because it's all algebra based. Find the extreme values of x to the power 2/3 on the interval -2, 3. So what are my first values to test?
-2 and 3.
So the endpoints, f of -2 is -2 to the power 2/3. We could do it a couple ways. So it's -2 squared, all that to the power 1/3. So -2 squared is 4 to the power 1/3 is equal to the cube root of 4. It comes from this translation. Whatever the denominator is, that's the root of your radical. If your exponent is a fraction, whatever the denominator is, that's the root of your radical. The next one is at 3. So we have 3 to the power 2/3, 3 squared to the power 1/3. So it's 9 to, which makes it the cube root of 9. Now, is there another point between -2 and 3 that'll work? How do we find that point? We take the function, find the first derivative of it. Bring the power down and subtract 1 makes it -1/3, which makes it 2/3 cube root of x. So is there an interior point where it equals 0? No. The only way a fraction can equal 0 is if the top is equal to 0. Since there's no x on the top, it can't. There's no interior point where it equals 0. So we look at where it's undefined, where f prime is undefined. F prime is undefined at x equals 0. So we take our critical values here, plug that into the original function. Let's look at our values we have here. So our absolute maximum and absolute minimum. So where's the maximum at? Where's the highest of those numbers? Okay, let's try something easier. What's the smallest of those 3 numbers? 0. What's the largest of those 3 numbers? Since they're
3.
both cube root, which number is bigger, 4 or 9?
9.
So this one's got to be the maximum. It says that there's nothing to think about. Just look at the numbers. There's just observation at that point. So your maximum's at the value x equals 3, and the minimum is at 0. Yeah, we won't have time to do another section. We're gonna start it.
Did you write that as 3 or did I write that as 3s?
No, that's the,
I have a question.
yes.
Could you go to the last example that we did? I got lost when we were solving for the critical points where we added e after finding the.
Okay, so this is the last one. So first thing we do is plug in the endpoints.
Yeah, I
That's what we
understand
did
that.
here. Now the critical values, we took a derivative of it.
Mm-hmm.
This is what we did first, we could have done a product rule first, but if it's easier, you can multiply it out
Yeah,
and then have a difference rule. But we still have to do the
the product rule right there.
product rule there anyway, so we should have just done it right here. So out of this, we have 10 times 2 is 20x minus 10x times ln x. The derivative of 20x is just 20
Mm-hmm.
minus the derivative of 10x ln x. Do the product
The
rule.
product rule. And we get 10 ln x and 10.
That's 10 ln x plus that. Notice I'm still keeping inside there.
Yeah,
So
and
we're
you
gonna
factor
factor
out
out 10.
the 10.
So ln x plus 1. So that's the function I'm using. I've set that equal to 0. So I have 20. I moved this whole equation to the other side. So I have 20 equals positive 10x times all this.
Okay.
Divide both sides by 10. I get 2 equals ln x plus
ln
1.
x plus 1.
Subtract 1 from both sides. 1 equals ln x. And so where does ln x equal 1?
At log ex.
Well, yeah, because we took the ln function, converted it back to the logs. ln is a
Right.
natural log, so it's log base e.
Mm-hmm.
So the e comes over to the other side, so x is equal to e to the power 1.
Okay.
So x is e to the power 1 is just e, so x is equal to e. I take that and plug it back into the original. This is my critical value,
Okay. And then you plug that into your
my original function.
original function. Okay. And then that's how you
That's
get
what I
your,
got.
and then that would be your
This would be, now this is one of my values I'm looking at to
okay.
see whether it's the highest is extrema or if it's a maximum or minimum.
Okay, so that's
So I
your
have to compare it to everybody
critical
else.
value from your critical point.
Yeah.
Okay. Okay, makes
Yeah.
sense.
So this is the value
That we got
from
whenever we
interior point.
yeah, okay.
Yeah, and the other two were my endpoints.
Okay, makes sense. Thank you.
Oh, thank you. Okay, let's go ahead and stop this one and start the next one.